you ask an AI to do step A, and then, you ask it to do step B.
Right.
But by the time you get to step C, it has, well, it's completely hallucinated some new objective, forgotten your original instructions, and just crashed your entire pipeline.
Oh, absolutely. It's so frustrating.
Yeah. And if you are building complex AI workflows, you know exactly that feeling, right?
Yeah.
Just watching a prompt chain spiral into this chaotic, unreliable mess.
I mean, it is the single biggest bottleneck in enterprise AI right now.
Yeah.
Because, we're relying on systems that are fundamentally designed to be conversational.
Yeah, they're chatbots, basically.
Exactly. But we're trying to force them to run these critical deterministic software processes. And those two things, they're just inherently at odds.
So that brings us to the focus of today's deep dive. We are looking at this state-of-the-art research paper straight from IBM. It's called Agentics 2.0, Logical Transduction Algebra for Agentic Data Workflows.
Which I know the title is super dense.
Very dense. But the mission here is actually highly pragmatic, right? Because the goal is figuring out how researchers are moving AI away from being these unpredictable chatty agents.
Right, turning them into rigorous, scalable enterprise software.
Exactly. Because it feels like right now, using AI agents is kind of like managing a group of brilliant but incredibly distractible interns.
That is a perfect analogy, actually.
Right. You give them a task, they go off into a conference room, they start talking to each other, they get totally confused about the goal, and you just end up having to look over their shoulders constantly.
To make sure they are still on track.
Yeah. So our mission today is to figure out how Agentics 2.0 turns those unpredictable interns into a highly efficient, predictable assembly line.
And the reason we really have to build that assembly line is because true enterprise scalability requires, well, a fundamental shift in how we view the underlying models.
Okay, what do you mean by that?
So the authors of this paper argue that we have to stop treating AI inference as a conversation, like entirely. We have to start treating it as a strict mathematical function.
Okay, let's unpack this, because before we get to the actual assembly line solution, we need to diagnose exactly why the interns are failing in the first place.
Right, the root cause.
Yeah. The paper talks about the current state of agentic workflows. So things like prompt chaining, black box planners, multi-agent systems where different AI personas just talk to each other.
Which is how most people build these things right now.
Exactly. And the authors claim these fail because of an anthropomorphic perspective, meaning we're treating the LLM as a person, with a role, communicating via natural language.
Yes.
But wait, isn't the whole magic of an LLM that we can just talk to it like a human? I mean, are they arguing that our natural language approach is actually what's holding the technology back?
What's fascinating here is that, yes, it is exactly what is holding it back in a production environment. Yeah, I mean, natural language is incredible for ideation. If you want to brainstorm marketing copy or draft an email, that flexibility is great.
Super helpful.
But flexibility is the enemy of a software contract. Think about a multi-step workflow. If you rely on natural language, you basically have no verifiable control flows.
Because it's just text.
Exactly. If an AI agent misunderstands an instruction in step 2, it doesn't throw a standard error code like normal software would.
Oh, right. It just keeps going.
Just silently passes a beautifully written, grammatically perfect, but entirely incorrect paragraph over to step 3.
And step 3 has no idea it's bad data. It just accepts that information as fact, processes it, and passes the compounded error to step 4.
That is the silent failure. The text looks plausible. Syntactically, it passes the eye test. But semantically, the meaning is completely corrupted.
Wow.
And that results in a total lack of software reliability and observability. You just cannot scale a system like that because you still require massive amounts of persistent human oversight to check the work at every single stage.
So the chatty conversational nature of the AI becomes a massive liability.
Exactly. It's a bug, not a feature for enterprise workflows.
So if the conversation itself is the problem, what is the fix? I mean, this is where the paper introduces its core solution, which they call logical transduction algebra.
It's quite a mouthful.
It really is. They want to shift away from conversational prompts and move toward what they call transducible functions, which honestly sounds like something pulled out of a theoretical physics textbook.
It does sound intimidating.
So what does that actually mean for a developer on the ground?
Well, the terminology is academic, but the mechanism is surprisingly elegant. A transducible function is simply an LLM inference call, that has been formalized into a typed semantic transformation.
Okay, a type semantic transformation.
Right. So in the Python programming ecosystem, developers often use something called Pydantic schemas.
Oh, yeah, to define the exact shape data needs to take.
Exactly. So instead of writing a prompt that says, please write me a summary of this document, you are mathematically forcing the AI to output data that perfectly fits a highly specific, predefined structural contract.
Okay, and the paper actually outlines 4 strict properties that this function has to meet to work, right?
Yes, for very specific rules.
So the first one is that it must be typed, meaning it just has to return a valid schema. Like, if the software contract asks for an integer, the AI cannot return a polite sentence that contains a number.
Right, you can't say the total is 42.
Yeah, it must return only the integer 42. If it doesn't, the function just straight up rejects it.
Exactly. And then the second property is explainability. The function cannot just output the final answer in a vacuum. It must explicitly generate a structured explanation of how it arrived at that answer.
So it has to justify its work.
Exactly.
Yeah.
This prevents the model from, leaping to conclusions without a logical chain of thought that a human or even another piece of code can audit.
Okay, let's talk about the last 2 properties, because this seems to be where the real enterprise value kicks in. The third is local evidence, meaning the AI must use a specific non-empty subset of the input data to compute its answer.
Right.
And the fourth is provenance, meaning there has to be an explicit mapping that traces the exact output back to the specific input evidence it used. So how do those 2 actually work together in a real-world scenario?
So let's look at the credit risk assessment example from the paper to kind of ground this. Imagine the input type model's a loan application.
Okay, got it.
The raw data we feed into the system includes an applicant's name, say Smith. It includes an income of $60,000, a debt of $25,000, and a credit history string that notes a late payment in 2021.
Okay, so that's the raw, unstructured data we're handing to our theoretical intern.
Right. Now we apply our transducible function. The required output type here is a formal credit evaluation. And let's say the output gives a risk score of 62 and a risk class of medium.
Okay.
But because we are enforcing those 4 properties, it doesn't just hand you the score. It provides the provenance.
Ah, so it maps it back.
Exactly. It explicitly maps its output back to the input, declaring programmatically that it used the debt, income, and credit history slots to calculate that score. And it completely ignored the last name slot.
Which makes sense, obviously. It shouldn't be factoring in someone's name when calculating financial risk.
Precisely. And finally, it provides the explanation field required by the schema. It would say something like, the debt-to-income ratio is moderate, and a historical late payment increases the overall risk.
You know what it almost feels like? It's like when you ask a kid for the answer to a math problem.
Oh, that's a good way to look at it.
Yeah, you're essentially forcing the AI to show its work on the chalkboard. It can't just shout out, score 62, and expect the software to accept it. It has to prove exactly which numbers it looked at to get there and map the logic it used.
And this gives developers what the authors call semantic observability.
Semantic observability.
Right. In a traditional prompt chain, if an AI hallucinates a detail like maybe it imagines a bankruptcy that isn't anywhere in the input data, it's incredibly difficult to catch that until the very end of the line when a human reviews it.
Yeah, because it's just buried in a paragraph of text.
Exactly. But in this algebraic framework, if the AI hallucinates, the provenance trace will immediately flag it. The output simply won't map back to the valid input slots.
Wow.
Yeah, the framework takes the invisible reasoning process of the LLM and makes it visible, trackable, and verifiable by the code itself.
Okay, so that covers the theoretical algebra part. But how do we actually build this? Like, we need to transition from the mathematical chalkboard to the physical Agentics 2.0 framework. How do researchers put this concept onto an actual software assembly line?
Well, Agentics 2.0 is built as a lightweight Python native framework.
Okay, Python, the standard.
Yeah, and its core design philosophy is treating typing as computation. It takes unstructured data, like a messy block of raw text or a dense CSV file, and parses it directly into a structured Python type through a process called canonical type transduction.
And what's wild is how they actually implemented this in the code. I was reading this, and they actually hijacked standard Python math operators to make logical transduction a first-class citizen in the code itself.
Yes, It's very clever.
Yeah, they use the less than symbol, the operator for transduction, that maps one type to another.
Right.
And then they use the at symbol for composing different types together, and the and symbol for merging types. Plus, they created a at transducible decorator that you can just wrap around asynchronous Python functions.
And the operator is really the workhorse of the whole framework here. You define a source type on one side, let's say a question schema that holds a prompt and some multiple choice options.
Okay.
And on the other side, you define a target type and answer schema that requires a specific valid choice. By placing between them, you create a stateless, asynchronous function.
So you're basically instructing the framework to force the input to transform into the exact shape of the output.
Precisely.
Here's where it gets really interesting to me, though. If I understand this right, the operator acts like a rigid mold, right? A magic wand. I have messy question on the right, I apply Ave, and it forces out a perfectly clean answer on the left.
That's the idea.
But what happens under the hood if the LLM just refuses? Like, what if the AI gets confused by the prompt and decides to generate a helpful conversational paragraph instead of the strict schema the operator is demanding?
So if the model's output is ill-formed and breaks the structural contract, the framework doesn't try to politely parse the conversation.
This doesn't try to salvage it.
No. It triggers a hard software error. It raises an exception and crashes that specific operation entirely.
Which sounds bad, but in enterprise software, a hard crash is actually infinitely preferable to silently passing bad text down the pipeline.
Exactly. You want the system to throw an exception immediately. That way, the surrounding code can handle the error programmatically.
Like maybe it retries the prompt automatically or flags it for human review.
Right. That is far better than finding out a week later that your AI generated a quarterly report based on a hallucinated metric that just silently slipped through the cracks.
Yeah, totally. And this framework is designed to handle this exact process at a massive scale using MapReduce semantics. Let's look at how that scales up, because this is cool.
Yeah, the scaling is where it really shines.
So the map phase takes this transducible function and applies it to a huge collection of inputs independently, all at the same time. Like, imagine you have 1,000 customer reviews.
Okay, 1,000 reviews.
The map function dispatches 1,000 mini-agents asynchronously. Each one processes a single review simultaneously, forcing it into a clean schema.
And then you move to the reduce phase.
Wow.
This takes that massive collection of processed, perfectly structured outputs and aggregates them into a single synthesized result.
Okay.
That might be a global summarization of the sentiment or a consensus formation or even a voting mechanism.
Wow.
And because every single map step maintains strict provenance and local evidence, you can trace a claim in the final global summary document all the way back down to one specific sentence in one individual customer review.
It really is a highly coordinated assembly line. That's amazing. But, we have the theory and we have the Python framework. But does this strict algebraic approach actually perform better than the chatty interns out in the wild?
Well, they tested it.
Yeah, the paper puts Agentics 2.0 to the test on a benchmark called Discovery Bench. What exactly is the system being asked to do here?
So Discovery Bench is an extremely difficult data-driven discovery task. The AI is handed raw data sets, usually CSV files containing hundreds or thousands of rows, along with some basic metadata.
Okay, so just raw tables.
Right. And the objective is to derive a complex scientific hypothesis from that data.
Oh, wow.
To do that, the AI has to identify the correct context of the data, extract the relevant variables, and then figure out the specific relations between those variables. The final hypothesis structure is essentially this complex tree of sub-hypotheses.
That is a brutal test. I mean, it is not just summarizing an article. It is being asked to perform actual scientific discovery from raw data tables. How did the researchers configure Agentics to tackle something that complex?
They implemented a two-stage MapReduce pipeline. The map stage sweeps across the different sources to collect intermediate evidence. It literally takes the raw CSV tables and parses them directly into strict Pydantic types without any human annotation or cleaning.
Just straight into the types.
Yeah. Then, the reduce stage takes all of that newly structured intermediate evidence and synthesizes it into the final scientific hypothesis.
And the results were definitely striking. I was looking at this. They ran an Agentics both configuration, which pulls evidence from both structured data and baseline React agents.
Yes.
And it scored an average of 37.27 on the benchmark.
Hmm.
And to put that into perspective for you listening, the best-known baseline for this specific test using a standard conversational React agent was only 33.7.
Right.
So the rigid assembly line clearly outperformed the conversational agent.
It did, but the nuances of where it succeeded and failed are actually very revealing.
Oh.
The framework performed exceptionally well on datasets related to archaeology and the introduction pathways of non-native plants.
Okay.
It was easily able to pull the correct context and identify the right variables from the raw tables, forcing them into the correct schemas.
But there were two massive weak spots. First, it failed completely when handed massive files. There was one dataset called Incels Incarceration that had over 12,000 rows.
Yes, that was too much for it.
The system just couldn't process it. It was great with manageable files, but broke on the huge ones. But the second failure point is what I find really fascinating. The agent was excellent at finding the variables in the tables, but it struggled significantly with extracting the correct relations between those variables.
And we have to look at why that happens. Finding a variable in a table is fundamentally an extraction task. It's essentially named entity recognition.
Right, just finding a word.
But determining how temperature affects plant growth based on thousands of rows of data requires complex statistical reasoning. It requires holding the entire data distribution in the context window and understanding how those extracted pieces of data interact with one another.
So, wait, if it can identify the variables perfectly but fails to understand how they relate, is that a flaw in the Agentics framework we just spent all this time breaking down, or is it a limitation of the large language models themselves getting overwhelmed by the data?
This raises an important question, and it points directly to the boundary between the framework and the model. Agentics 2.0 is responsible for the data routing. The MapReduce pipeline worked flawlessly to extract the raw data and push it into the correct mathematical schemas.
So the pipe itself didn't break.
Exactly. The failure in relational logic points to the current limitations of the underlying LLMs. When you ask an LLM to perform complex relational reasoning over large multidimensional datasets, its cognitive reasoning often breaks down.
Oh, I see.
The framework ensures the AI looks at the right data, but it cannot magically grant the AI the ability to reason perfectly about it.
So if it's struggling to understand how variables interact in a CSV file, I'd imagine it completely falls apart if you ask it to do something highly structured, like writing actual database code.
You would think so, yeah.
Which brings us to the second major test in the paper. The researchers wanted to see how the framework handles highly complex logical reasoning, so they ran it through the Archer benchmark. What makes Archer so uniquely difficult?
Archer is a bilingual natural language to SQL benchmark. It asks the AI to take a natural language question presented in either English or Chinese and translate it into executable SQL database code.
Which is notoriously difficult.
Very. Because it goes far beyond simple database lookups, it requires arithmetic reasoning, common sense reasoning, and hypothetical reasoning just to capture the user's true intent before it even writes a single line of code. Historically, LLM scores on this benchmark are incredibly low.
Yeah, translating a vague English question into strict SQL, it almost feels like trying to turn a really abstract poem into a binding legal contract.
That's a great way to put it.
It is incredibly rigid. One misplaced comma and the entire database query just crashes. How did the Agentics 2.0 framework approach this translation?
They build what they call a reasoning validation agent, which is a multi-step transducible workflow. First, the agent searches a training database to extract a few-shot dataset of examples that share the exact same reasoning type as the user's question.
Okay, finding similar problems.
Next, it analyzes those specific examples to formulate a custom strategy. Then, it generates the SQL query. But it doesn't stop there.
Right.
It verifies that query for syntax errors against a dummy database engine. Finally, it performs a semantic validation step, checking its own generated SQL code against the initial strategy and thoughts it developed.
So it is actively looping back to check its own work against its original plan. If the dummy database throws a syntax error, the transducible function forces the model to read the error, update its internal state, and rewrite the query until it fixed the schema contract.
Exactly.
And the results here were actually fantastic. The Agentics implementation outperformed almost all of the leaderboard submissions, except for one highly specialized framework that was custom-built strictly for planning.
Which is a huge win for a generalized framework.
Totally. They also ran model comparisons and found that OpenAI's GPT-03 beat Google's Gemini 3 Flash, specifically in the queries that required both arithmetic and common sense reasoning simultaneously.
Yeah, the more complex the reasoning requirements, the more the choice of the underlying foundational model actually matters.
But looking at the big picture here, does the success on this Archer benchmark prove that giving an AI a strict algebraic framework actually makes it better at reasoning?
Yes, and this is arguably the most important insight of the entire paper. When you leave an AI in an unconstrained conversational state, it expends a massive amount of its available compute power just figuring out how to format its response.
Oh, wow. I didn't think about that.
Yeah, it's trying to maintain its persona, deciding how to structure its paragraphs, and figuring out how to transition from one thought to the next.
Is acting.
Exactly. By constraining the AI's boundaries through the transducible algebra, you completely remove that cognitive formatting burden. You free the AI to focus all of its computational power purely on the actual logic and reasoning task.
That makes so much sense. We have covered a lot of Bent's ground today, so let's summarize the journey for you.
We started with the core problem. Conversational AI agents are essentially distracted interns. Yes, very distracted.
They hallucinate data, they fail silently, and they are impossible to scale in an enterprise environment because of their anthropomorphic design.
Yeah.
We treat them like people, and they fail like people.
And the solution IBM's researchers propose with Agentics 2.0 is to treat AI as a strict mathematical function using logical transduction algebra.
Right, by enforcing transducible functions that demand type schemas, local evidence, and clear provenance, we force the AI to show its work. We move from hoping the AI generated the right answer to mathematically proving it got it right through semantic observability.
Yes.
We saw how this MapReduce Python framework operates in practice, hijacking standard operators to build an assembly line that beats out traditional baselines in both data discovery and highly complex reasoning translation like the Archer SQL benchmark.
The primary takeaway is clear. If you are building AI tools for the enterprise, it is time to stop writing endless, fragile prompt chains and start thinking like a traditional software engineer. The future of reliable AI isn't about building a more polite chatbot. It's about building better mathematical contracts.
It feels like the assembly line has finally arrived for artificial intelligence. But, looking at how tightly controlled this new paradigm is, it does make me wonder.
Yeah.
If we completely strip away the conversational human element of AI and constrain it entirely to strict algebraic functions, do we lose the chance for those weird accidental hallucinations that sometimes lead to brilliant out-of-the-box discoveries?
That is a really profound point.
Right. Like, can true serendipitous innovation exist in a perfectly constrained system? Definitely something for you to mull over as you look at your own AI workflows. Thank you so much for joining us on this deep dive. We will catch you on the next one.